Okay, so now we're back for our very last thing we're going to cover for Algebra 1 this school year, and that is operations with radicals and exponents. And now we're going to start using those exponent rules. And so the exponent rules are the product rule. As long as our bases are the same, when we times those bases together, we can add these exponents. So that's our product rule. Power to a power, I can distribute an exponent inside, and when I do that, I multiply them. The zero exponent rule, anything to the zero power is really 1. The quotient rule, as long as we have this same base, I can subtract exponents. And the negative exponent rule, anytime I have a negative exponent on the top, I can move it to the bottom, it becomes positive. If I have a negative exponent on the bottom, I can move it to the top and it becomes positive. So how are we going to see this? Well, our first problem, I have 2 to the 1/2 power times 2 to the 3/2 power. So we double check, we have the same base of 2, which means by the product rule, I can add these exponents. So this becomes 2 to the 1/2 plus 3/2. And 1/2 plus 3/2, because they have the same denominator, we add the top numbers. And so this becomes 2 to the 4/2 power. And 4/2 is really just 2. So 2 to the 2nd power, which is really the answer of 4. And now we've just simplified that. Okay, on our next one, I have 5 to the 1/4 power times 5 to the 3/2 power. So because they have the same base of 5, I can add those exponents. So 5 to the 1/4 plus 3/2. Now the problem here is I can't add those because they don't have a common denominator. But I can change my second fraction. And I could change that by timesing top and bottom by 2. Really, I'm multiplying by 1, just like we did when we rationalized the denominator. I'm just giving that fraction a makeover, so that way I can purposely do operations. So now this becomes 5 to the 1/4 power plus 6/4. And now I can add those together. So this becomes 5 to the 7/4 power. And so now I can go ahead and start doing some stuff that I had talked about before. So I could look at this several different ways. Method number 1 would be, okay, this is the 4th root of 5 to the 7th power. So 1, 2, 3, 4, 5, 6, 7. I'm having problems writing. And then all I need is, because it's the 4th root, is 4 5s to pull out. So I get a 5 to the 4th root of 5 to the 3rd, which is 125. So I could look at it like that. Or I could go ahead and we could break this up. This is really, here I'm going to bring this down, maybe bring this up here. So this is a 5 to the 7/4, which is really 5 to the 1 3/4. So you're starting to see that. And so 5 to the 1st power times a 5 to the 3/4 power, which is really a 5 times the 4th root of 5 to the 3rd, which is 5 times the 4th root of 125. So lots of ways to think about things and use these operations to help simplify. The more versatile you are, the easier it is. So let's go ahead and look at another one. We have 3 to the 3/2 power raised again to the 4th power. So again, I've got this value raised to the 4th power, so it's like a power raised to a power. And with that rule, we multiply. So this is really going to be a 3 times a 3/2 times 4. And so this really becomes 3 to the, I can put 4 over 1, and I times the top, I times the bottom. Well, 12 over 2 is really just 6, so this is 3 to the 6th power, which is really in need of a calculator to calculate, because I'm not going to be able to do that in my head. So 3 to the 6th power is 729. So totally simplified by using our operations. And that's why we like being able to do this, is because we can simplify stuff to be able to work with this. So our next one is 5 to the 3/2 power over 5 to the 1/2 power. And because it's division, so when it's multiplication, we added. When it's division, we subtract. So that's a relationship. Multiplication turns into addition of exponents. Division turns into subtraction. And so this is really now going to be, and I can do that because these are both a base 5. If they weren't the same base, there's no way I could combine them. So this will be 5 to the 3/2 minus the bottom exponent 1/2. Luckily, they are the same denominator, so I can go ahead and combine that. So 3 minus 1 gives me 2. So this becomes 5 to the 2/2 power, which is really just 5 to the 1st power. So this is really just 5. Okay, and so now let's go ahead and look at another property. I have 25 to the negative 1/2 power. So with negative, that means I move it to the bottom. So now it's really 1 over 25 to the 1/2 power. Since I know that the 1/2 power is really, I can actually do this another way. I could say that 25 is really 5 to the 2nd power. And that's being raised to the 1/2. So now I can times those. So this could be a 1 over 2 times 1/2 is really 1. So this is 5 to the 1st power, which is just 5. So this is really 1/5. I could also look at it as, so what's another way I could have done that? So instead of 25 to the 1/2 power, I could have wrote that as 1 over the square root of 25, because I know the 1/2 power really means that it's a square root, and 25 to the 1st power, and then the square root of 25 is 5. So there's another way I could have figured that out. And math is all about multiple ways of figuring it out. So you've got to figure out what works best for your brain and that you can consistently use correctly. Okay, need another color, so that way I'm not blended into everything else. Okay, the square root of 2 times the 3rd root of 2. So let's go ahead and look. The square root of 2 is really 2 to the 1/2 power. And that's being times by 2 to the 1/3 power. And normally you wouldn't think that you can combine these, but now that we know our rules, I can write those as fractional exponents, and to be able to add those, so I can combine them because this is a times and they're both the same base. So this is really 2 to the 1/2 plus 1/3. And I can add those if they have a common denominator. So let's make them have a common denominator. So this is going to be 1/2 is really the same thing, common denominator with 6. So 1/2 is really 3/6. 1/3 is really 2/6. And so now when I combine them, I get 2 to the 5/6 power, which really means that this is the 6th root of 2 to the 5th. Why did I write it like that? Because if you usually start in radical form, you should finish in radical form. But really read your directions just in case, because they're going to want a specific form. And then 2 to the 5th power is really 32. So this is really, I don't know why I wrote 6 or 3. So this is really the 6th root of 32. Okay, so let's see, what else do we have working on? Oh, more and more examples, because really, honestly, when you're working on this on your own without me walking you through it, it's helpful to have you have lots of examples. But at this point, I'd say look at what you have and try this on your own. So pause your video, try it on your own, and then watch me walk through it to really see, do you know what you're doing, do you not, and all that good stuff. Okay, so hopefully you've paused your video, you've worked this out, and now you're just ready to double check. So let's go ahead and double check. So we have 3 to the 3/2 times 3 to the 5/2. So because these are the same base, we're going to add those exponents. So 3 3/2 plus 5/2. So this is going to become 3 to the 8/2, which is 3 to the 4th, which is really the number 81. Okay, so let's look at another one. 5 to the 1/3 times 5 to the 5 sixths. So again, same base, so we add those exponents. Problem is they don't have the same denominator. So we're going to have to rewrite that, and so this is really going to be 2 sixths plus 5 sixths. So this really becomes 5 to the 7 sixths power. And I'm going to go ahead and split this up as 5 to the 1 1/6 power. That way it's 5 times 5 to the 1/6. So I'm using that property backwards. Sorry about that. So this is really 5 times the 6th root of 5. So I've got several answers. If I want to leave it like that, I can. Or I can turn it into this. These are all possible answers depending on what they're looking for in the directions. Okay, so next one, 7 to the 2/3 raised again to the 12th. So we multiply those exponents. So this becomes 7 to the 2/3 times 12. So this becomes 7 to the 24/3, which is really 7 to the 8th power. Whew, that's going to be a big number. What is 7 to the 8th power? 5,764,801. Okay, so let's look at our next one. 5 to the 3/2 over 5 to the 4th. So because this is division, we're going to subtract those exponents. So 5 to the 3/2 minus 1/4. And I can't subtract now because we don't have a common denominator. So this will really be 5 to the, 3/2 is really 6/4 minus 1/4. So this becomes 5 to the 5/4. And we can leave it like that if we want to leave it as a rational exponent. Or if we turn it into a radical, this will be 5 to the 1 1/4, which is really 5 times 5 to the 1/4, because this is my 5 to the 1st, which is really 5 times the 4th root of 5. So there's our radical version. So again, always double checking what are they asking for. 8 to the negative 1/3 power. So we're going to move that down below. And so this is really 8 to the 1/3 power. And so one thing that I'd want to do is I want to see, is 8 really a number to the 3rd power? So this is what I really like about rational exponents, is instead of playing with, okay, this times this to the 3rd power is really that, I can actually type in my calculator 8 to the parentheses 1 divided by 3 power, and that'll tell me what that value is. And 8 to the 1/3 power is really 2. So what this tells me is that 8 is really 2 to the 3rd power, and that's being raised to the 1/3. So when I times, I get 1/2, because 3 times 1/3 is 1. So this is really 2 to the 1st power. And so then for our very last problem, we have the square root of 3. So this is 3 to the 1/2 power times the 4th root of 3, so 3 to the 1/4 power. So I'm going to have to go ahead and combine these. So 3 to the 1/2 plus 1/4, which means I need a common denominator. So 3 to the 2/4 plus 1/4, which is 3 to the 3/4 power, which is really the 4th root of 3 to the 3rd power. And 3 to the 3rd power is 27. So, whoops, didn't write a 4, 4th root of 27. So this is good, or this is good. Okay, so that's what we're going to be working on. And I'm hoping to spend a couple, maybe 2 days on this, so that way you get lots and lots of practice with it.